Alright, Unit 5, Inequalities, Day 1. Today what we're going to focus on is graphing radical inequalities. And we're going to have to remember that there's a domain restriction. When you're graphing it, there's a place where the radical equation or the radical graph starts, and therefore the solution set ends at that starting point. It'll make more sense when we do graph a couple of these things. Basically what it includes is drawing a vertical line through the point where the square root function begins, and that is a boundary to the solution set of the overall inequality. So before we get started, let's do a simple review. Less than or greater than is a dotted line. Later on, when we get to the number line, that's going to be an open circle. And of course, less than or equal to, greater than or equal to is going to be your solid line. Closed circle. Now, as you will notice from the restricted domain, that is also going to hold true for the line that you draw for the restriction as well. We're going to use transformations of parent functions here to help us solve this problem. Remember your critical values of the parent function y equals the square root of x, and those are going to help us accurately graph these pictures. So that's up 3, right 2. So I'll go right 3, up 2, find the starting point of my graph. I'm going to go over 1, up 1 using those critical values, over 4, up 2, and then I'll go over 9, up 3. Because this is less than or equal to, that is going to be a solid square root. And because the domain of this does not exist to the left of the number 2, we are going to draw a vertical line through that point to help us establish the boundary that restricts the solution set of this overall function. So, take my highlighter and fill in the solution set, and then we will further describe the solution set using domain and range in interval notation. So the solution set to this is that shaded area. Notice it does not go beyond this because any value to the left of the starting point of the square root is undefined. That is why there's a boundary line there. Because it's less than or equal to, both the boundary line and the function itself are solid. And we'll go ahead and relate the solution set in terms of domain and range in interval notation. So the solution set to this inside the shaded region is going to begin at the number 2 and continue all the way through to infinity. What does this mean? Any point inside of the shaded region is a solution to this inequality because it goes down to negative infinity and this curving line never goes horizontal. That means the range of my solution set will be all real numbers, negative infinity to positive infinity. Alright, we'll try this again. Now we're going to transform this left 4 and up 1. There's no stretch or compress, so our critical values are going to be these. Now because it's less than, or sorry, greater than, we are going to have a dotted line for both the function and its boundary. Remember, because the function is undefined beyond the point -4, we will not have that be part of our solution set, which is why we are drawing this boundary line here. The solution to this is going to be greater than the line, but not equal to it. That's what the dotted is for. We'll also express this in interval notation as well. The solution set The domain of the solution set is going to be -4, not included, to infinity, and the range is going to be 1 to positive infinity, not included. Continue on with number 3. Now we're getting some different transformations, causing some different movement on the graph. Please remember, in parent functions, the coefficient of x must be +1. Because there are no parentheses around the value x minus 2, we must assume that the coefficient of x is -1. So we need to rewrite this and factor out the negative value, leaving us x plus 2 minus 4. Now we have 3 transformations going on. Left 2, down 4, reflection across the y-axis, or reflection horizontally. So we'll go over 2, down 4, put our dot, and we have no stretch or compress. When normally we would go to the right, now we'll reflect across to the left, over 1, up 1, over 4, up 2, and over 9, up 3. Next, we have to identify the less than, so that is going to be a dotted line in this direction. And recognize the boundary begins at -2. There are no defined values on the square root function greater than -2, which is why we define that boundary line using that. Because it is less than, we will shade below the function, and our solution set lies here. The solution set in interval notation will begin at -infinity. Please make sure you go with your smallest values first, and will go all the way to the number -2, not included. The range in interval notation is going to be all real numbers, -infinity to positive infinity. Right, question number 4. Another reflection. Make sure you identify it. The coefficient of x is -1. Notice also we've changed into function notation. Not a big deal. F of x stands for y. I'm going to go ahead and switch the order of my x and my 2. And my 3 transformations are right 2, up 3, reflect horizontally. So I'm going to go ahead and move right 2, up 3, and reflect this guy rather than going to the right, back to the left again. Over 1, up 1, over 4, up 2, over 9, up 3. Now I'm back to that solid line. And because the square root function does not exist to the right of the number 2, I will be drawing in my boundary line. Because this is greater than, the solution set is going to be above the square root curve. The solution in interval notation is going to be -infinity all the way to 2. This time it is included. The range will begin at 3, included, and continue to positive infinity. Please complete questions number 5 and questions number 6 on your own. Note that they do include transformations that include stretches and compressions, so please be mindful of that and graph your critical values appropriately. We will go ahead and skip now down to questions number 7 and question number 8. Now, we're looking at a slightly different problem here, so we're not going to be graphing it on the Cartesian coordinate. Instead, we'll just use a number line. All right. Sometimes it does help to see it on the graph though as well. because it does help give it a little bit more meaning. So we'll go ahead and do that so you can take a look at it. Remember, the coefficient of x must be 1, so we're going to factor that 4 out of there. That just gives us a compression. So write 1, and then I get a horizontal compression, or a horizontal stretch, or horizontal compression of that. So we're going to be basically here and here, and so you get this very flat, level looking guy like that. And then we want to know the place where it is less than or equal to 4. Okay? And so that's going to be the place where we determine what our answer is going to be. The way that you do this is by first simplifying or solving for x. Getting rid of the square root gives me 4 times x minus 1 less than or equal to 16. Divide by 4, x minus 1 less than or equal to 4, x less than or equal to 5. So on my number line, I'll go ahead and begin at the number 5. It will be a closed circle, and it will go to the left. The other thing I have to recognize is that this thing actually has a starting point, and I have to be very mindful of that starting point because all values to the left of that starting point are undefined. Therefore, they are not part of the solution set to this particular problem. So I've got to understand the restriction on the domain is greater than or equal to 0. This is exactly the way it was taught last semester. This is exactly the same restriction we have. So please make sure that you understand that this is a previous taught idea, and you'll be doing this exact same thing when we're looking for solutions to all of these inequalities moving forward from here. That means that beyond the number 1, this function, this graph, is undefined and therefore will not exist. So I need to acknowledge that in my solution set. It will always be a closed circle at the restriction because of the fact that it can be equal to 0, but it cannot be less than 0. The solution to this problem is between the numbers 1 and 5. Writing it in interval notation, your solution is 1 to 5 included. Here on this one, we have a stretch and we have a reflection. So when we graph these, I'll go ahead and just do a quick sketch of them so you guys can see what it looks like. I will be here, heading in this direction for the first one, and I will be here, heading in this direction for this one. So in this particular problem, you'll notice that this graph, that's the second one, is above this graph, that's the first one, between this point, wherever they intersect, and this point, where this graph ends. So we are looking for the distance from here to here, and we're going to represent that in interval notation, both on a number line. The way that we'll be doing that is by squaring both sides of the equation, here, and solving for x. 2x plus 5 is less than 2 minus x. Add my x's, subtract my 5, I get 3x cancels, less than negative 3 cancels. So that means x is less than negative 1. I'll begin over here at negative 1. That will be an open circle because there is no equal to there. And now I've got to determine where this particular graph ends. Since this is that one, I will go straight there. 2x plus 5 is greater than or equal to 0. Minus 5 to both sides. 2x greater than or equal to negative 5. So x must be greater than or equal to negative 5 halves for this to be defined. Therefore, the stopping place for my solution set will be at negative 5 halves. Writing that in interval notation looks like this. Include negative 5 halves because that's the restriction on the domain. It will always be included. And negative 1 is excluded because of the inequality symbol given. Please complete those two problems and have them ready to discuss, as well as any questions that you might have regarding this material.